All right, sorry for the delay. Today I'm going to be talking to you about a theory for an experiment which was done at the Meitner Institute a very long time ago. So the data is courtesy of Alan Tennant. And I'm going to cover machine learning in two ways. One is as one input, which was actually important for this analysis. And then in the outlook, I'm going to have something like a small wish list if time allows. Let me just... Okay. Since this is quite a heterogeneous audience, I'll very quickly breeze through an introduction about U1 spin liquids in 3 dimensions and introduce the system that we're studying.
Yeah, share the results.
Okay, sounds okay. And it's basically an example of how a gauge field emerges in condensed matter. And the research program that we've been following for a few years now is to say, so for many years, the question was, how do you get a system described by an emergent gauge field? And now that we have some, the question is, what is the new physics they inhabit? And I'm going to show to you one particular...
share your whole screen.
Okay, one particular phenomenon which I think is actually really neat and which has a very simple explanation.
Oh, come on, yeah, quick one.
Sorry. Okay. Okay. So, all right, very brief introduction. So I'm talking about a very simple magnet called spin ice. It's very simple in the sense the lattice, which is defined as an Archimedean lattice where all sides are equivalent to each other. This is known as the Pyrenean lattice, and the spins themselves are simple Ising spins. They can take on 2 values, either pointing out of the tetrahedron or into the tetrahedron. And the ice rule mentioned by Alan is that 2 spins point in and 2 spins point out of each tetrahedron. And the description, as I'll show in the next slides, is simple emergent magnetostatics. And this is, as I say, the simplest case that I know of an emergent gauge field in condensed matter physics. Okay. Why is it called spin ice? Well, the Bernoulli-Fowler ice rules in ice basically say that the oxygens, which are proton bonded, hydrogen bonded to their neighbors, have 2 protons sitting next to them. So if you draw a little box around this, around an oxygen, and you draw an arrow in the direction of the proton, then you find a tetrahedron with 2 spins pointing in and 2 spins pointing out. So we're going to use this as a description of the system. And then the big insight was that spin ice is neither ordered like a ferromagnet, nor is it disordered like a paramagnet. But actually, the ice rules can be cast in the form of an emergent conservation law. So if you basically think now of the spins as representing fluxes on the network defined by the centers of the tetrahedra, you see that it's basically an emergence-free, divergence-free field. So each node of the network, 2 fluxes come in and 2 fluxes go out. So this takes the form of a conservation law. So if you write the magnetic moments as mu, then the elastic divergence vanishes. And at this point, you can stop thinking and simply say, well, if I've got this, I know from electromagnetism or Helmholtz decomposition that I can write mu as curl A. And so this is just a microscopic transformation. The point now is that if you say, okay, what's the simplest theory I can write down, which involves a divergence-free field? Well, then it's basically simply the square of this Gaussian theory with where the divergence freeness is built in here. And then you can turn the crank, and what you find is that if you look at the neutron scattering structure factor, you expect to find pinch points. So this is a pinch point as opposed to a Bragg peak, which you get a ferromagnet, or a completely smooth structure that you get in a paramagnet. But a pinch point is basically something which is a 1/r³ correlation in 3 dimensions. And so experimentally, this was found. So theory versus experiment, you see these pinch points appear very nicely. So these pinch points are basically telling you that you've got an emergent gauge field in the system. And you see there's nothing fundamental about this. It just happens to come out of a very simple Ising model that the low energy theory is an immersion gauge field rather than photons, or God knows what. Okay, so that's it. So there's nothing fundamental in the sense of having gauge fields appear in condensed matter. It seems like an accident, but it's a completely natural thing to happen. Okay, if you've got an immersion gauge field, you can have excitations which are charged under the immersion gauge field. And so you might think, okay, I've got an Ising magnet, so the simplest low energy excitation I can think of would be a flipped spin. So I'm showing here basically this divergence-free gauge field. At each point, there are 2 arrows pointing in, 2 arrows pointing out. For simplicity of showing things, I'm only keeping 2 of these arranged head to tail, and now I'm flipping the spin, and then you see that there are 2 tetrahedra where you've got a net sink and a net source of magnetization. So, but if you flip further spins, you do not generate further sinks or sources. You just separate them, as you can see here. And so what you find is that actually the spin fractionalizes into point-like excitations. So this is a 3-dimensional system with point-like excitations. And these point-like excitations are sources and sinks of magnetization. Okay. If you work out their actual interactions, it turns out that they obey a Coulomb interaction, so 1/r energy. But the Coulomb interaction is not electric, E squared over 4 pi epsilon naught. It's actually magnetic, U naught over 4 pi times Qm squared, times Qm squared. Okay. So this is, so we've got an immersion gauge field, and we've got these particles which are charged under the immersion gauge field. And these are what we call magnetic monopoles because they've got a magnetic Coulomb interaction. Okay, so these are the basic ingredients. That was the introduction. And now I'm going to, if there are any questions you should ask now. Anything's unclear, because now I'm going to move on to dynamic. It's because it's going to be a dynamical experiment that we try to explain. Okay, I'd just like to say, so this is an example of fractionalization in 3 dimensions. The only magnetic system I'm aware of which is proven to be fractionalized in 3 dimensions, and until perhaps today, perhaps not until in a few months' time, also the only fractionalized system I'm aware of which is magnetic at all. Okay. So, standard model of classical spin isodynamics is extremely simple. You basically say spin flip is essentially the same as a magnetic monopole hopping from one tetrahedron to the other. And you can now say, okay, the simplest dynamics I can think of is essentially Monte Carlo dynamics. I try to flip every spin, and if this is possible without paying a lot of energy, then I flip the spin, and if it's not, I don't. There's only one free parameter there, the rate at which I try to flip spins. So this is 1/tau, parameterized by 1 parameter. And what you see is that a monopole can basically hop in 3 directions, because the 4th direction would involve a hop, which leaves you with a doubly charged monopole here, 4 spins pointing out. That's extremely costly, low temperatures, and therefore we suppress it. Okay, so this was already proposed 15 years ago, and it's actually been moderately successful. So if you look at the relaxation time in spin ice as extracted from AC susceptibility measurements, it's faster than exponential rise of low temperatures. It's actually reproduced, not quite, not perfectly, but you get an exponential rise out of this. The reason for the exponential rise is very simple. Monopoles are gapped, so they become exponentially sparse. Since spin flips are monopoles hopping and they're exponentially sparse monopoles, it takes exponentially longer for the system to forget its state. So that's here. This discrepancy is something that has been obvious for a long time, but there are a lot of uninteresting ways that this could come about, which is why we didn't try very hard to understand this. But then these experiments that Alan recognized, that Alan motivated and also recognized the importance of, came along. So here you see the power spectral density of the magnetic noise. So you can think of this as being proportional to the frequency times chi double prime. And if you just have randomly flipping spins, you get this kind of shape. So it's flat at low frequencies, and it decays like 1/omega squared at high frequencies. So the way you can imagine, the reason it's flat at low frequencies is basically when you're sampling a curve at a frequency which is much lower than the internal timescales of the system, then the frequency at which you're sampling no longer plays a role and things become flat. And whereas at high frequencies, basically, if your spin flips, if you're sampling at a frequency which is much higher than the spin flip, you're basically only sensitive to derivatives, and which is why you get a power of omega appearing here. So in this case, omega to the -2. So this is essentially, in this representation, this is a ratio. Okay. And the remarkable thing is that at low, moderately low temperatures, it's actually not a Lorentzian, but you get a power of omega to the minus 1.5. Okay, so now there are two ways of looking at this. So one is 1.5 is close enough to 2. Why are you wasting your time? So this is a reasonable point of view to take. And if this point of view that you take, then I suggest you go out and have a look at the sunset, because that's going to be much more satisfying. If you think about what happens in 3 dimensions, tell me examples where you get anomalous powers in 3 dimensions. Okay, it's extremely rare. Unlike in 2 dimensions, where basically costed Saulus ensures that you can have lots of drifting powers, in 3 dimensions, it's extremely rare. Now I'll show to you that this is a mechanism at work which is really quite special and quite unique. Okay, so this is when we decided to look at this in detail, and I think we imposed on the patience of Alan for a long time until we came up with an explanation, which took us really embarrassingly long, but we finally found one, and it's extremely simple. So this is also a little bit of a sociological observation. So everything's topological these days. Here, what we found is a symmetry based and it's completely local. And this is why it's so embarrassingly simple. If you look at a particular spin which wants to flip by allowing a monopole to hop across it, there are 2 symmetry distinct configurations. One is where these 3 spins are inversions of those 3 spins, and one where they are not. They appear in a relative rate of 2 to 1. If you look at the transverse component of the dipolar field exerted by these 6 spins, in 1/3 of the cases it vanishes, in 2/3 of the cases it doesn't vanish. Spin flip process is complicated in these pseudo spins, but at the end of the day, what certainly is true is that if you don't have a transverse magnetic field, you don't flip. So we estimate the ratio of these flipping times to be about 1,000. Being theorists, 1,000 is the same as infinity, so we basically just say this spin doesn't flip, those spins flip. This is the only thing we change, so this is what we call beyond the standard model of spin ice dynamics, and then we revisit the experimental puzzles. So these were the different curves. These are the best fits from the standard model, and now we just look at our model, and what we find is this here. So basically, the discrepancy hasn't completely disappeared, but rather than being a factor of 20, it's a factor of 2 roughly, and the anomalous behavior here is basically quantitatively reproduced. Okay, so the experimental puzzles, as a matter of practice, seem to be resolved by this model, and now we have to ask why. But before we do so, I'd like to ask, how can we be confident in the theory? Because you could point out that, well, these curves don't have a lot of features. So couldn't there be many theories which actually explain what's going on? So there actually is a large space of possible models, but notice, first of all, we haven't introduced any new additional parameters. We still got only this one spin flip attempt rate, and it's changed from what we had before. I'll say a word about this later, further down, but basically we still have only one global parameter for all the curves. Okay. The other thing is that we actually use the machine learned Hamiltonian from other data. So this is what one of the things that Alan put into this project. So in other words, we didn't have any bias from the Hamiltonian towards our explanation. We just took the Hamiltonian basically said this is fixed, and then we're going to work with it. We in fact did try quite a lot to play around with other Hamiltonians, and we did find one which reproduced the dynamics more or less, but it was clearly at odds with other experiments. And this shows how it's really important to have well-characterized model systems, not necessarily because a given system is particularly interesting, but because if you have a very well-characterized system, you basically don't have wiggle room to come up with incorrect theories to apparently explain things. One of the things that gave us particular confidence is that there had been the timescales that I mentioned for this that were extracted here were essentially obtained by assuming a model of the spin ice dynamics and then fitting that to AC susceptibility measurements, right? There were also direct measurements based on neutron scattering, and they found a spin flip rate which was considerably faster than 200 microseconds. So our new fit was already more than a factor of 2 faster, and the reason for that is very simple. If less spins flip, but the AC susceptibility is fixed, then they have to flip faster, okay? It's qualitatively very clear. And so we basically resolved that particular conundrum without even having set out to do it. We didn't even realize that they were related, but really the fact that less spins flip, as we said, it naturally accounts for that. It's worth emphasizing this is a purely dynamical phenomenon. If you use either of the two types of dynamics for thermodynamics, you get identical answers. Both dynamics are ergonic. Okay, the explanation is percolation. So you know what percolation is. So let me just skip that explanation and go straight here. Explain how critical percolation explains these things. Okay, so as I said, monopoles hop is the same as spins flipping. The monopoles hop on the dual lattice of the pyrochlore, which is a diamond lattice, which has a coordination form. For energetic reasons, they can only hop in 3 directions. But then of the remaining 3 spins, as I said, on average, a third can't flip, so the average coordination is 2. You immediately see average coordination 2 is not a 3-dimensional system. It's in fact a straight line. So something weird seems to be going on there. If you model this in more detail, what you actually find is that the cluster on which the monopoles can hop is very close to a critical percolation cluster. I'll characterize that in a few minutes. So in other words, the monopole actually moves on a critical percolation cluster, and critical percolation clusters are fractals. Okay? A random walk on a fractal embedded in 3 dimensions looks like subdiffusion. And subdiffusion transformed into the time domain by saying motion of monopole corresponds to a spin flipping gives you the anomalous power in the noise spectrum. So that's it. Basically, the system self-organizes to have the monopoles subdiffuse on a fractal cluster, and this is the property of the fractal cluster which feeds through into the unusual signal that I showed. So I'm going to justify these statements in more detail now, but this is basically the story. Okay, so if you look at the fractals on the clusters in which the system moves, so for the standard model dynamics, these are pretty dense. For beyond the standard model, they're a lot sparser. So after 12 hops, the monopole can only move those sites, visit those sites here. Statistically accessible after n steps. At very long times, it's always n cubed. As I said, we're not sitting exactly at percolation, we're sitting close to percolation, but standard model dynamics, this n cubed is basically reached already after a few steps. So when lattice scale physics becomes invisible, whereas here you get a much bigger crossover regime. And in fact, if you tune to be sitting at exactly at percolation, you get those sign crosses, and you see that they agree with the simulations essentially up to some crossover scale, which is roughly given by number 14. So for 14 steps, the monopole actually thinks it's living on a critical percolation cluster. Okay? And up to then, it really quantitatively is described by the critical percolation cluster. Okay? So the monopole noise, just to explain how things go here. So monopole motion links spatial motion to magnetization fluctuations in the time domain. We're now looking at a single monopole so that the plateau at small frequencies is cut off or shifted to the left. So large distances is small frequencies. So at large distances, we expect normal behavior. So beyond the standard model gives you omega to the -2. But at intermediate scales and short scales, we actually have the short time behavior, and that's this omega to the -1.5, which is the same as the random walk on the fractal. Okay, so this omega to the -1.5 basically is a very direct measure of the fractal exponent of this percolation cluster. Okay, and I should say it's not actually 3/2, it really is -1.5. This is not an exact rational number as far as is known. Okay, I mentioned that this is subdiffusion of monopoles. So here we're showing the root mean squared displacement as a function of time. So you see it starts off with 1 power and it eventually crosses over to normal diffusion where r squared goes to the square root of t. But notice that for quite a long time, it actually scales like the 4th root of t. So it's a very significantly different exponent. And this time is roughly 10 to the 3 tau fast. So that's a fraction of a second. So this is really a macroscopic time scale. And again, if you ask yourself, how many mechanisms do you know that particles in 3 dimensions subdiffuse? You'll have a hard time naming many. In fact, we spend a lot of time trawling through the literature looking for mechanisms, and we basically didn't find any. So yeah, it's basically a geometric critical phenomenon that's being probed. Okay, so how much time do I have left?
You have 10 minutes.
10 minutes, okay, very good. So given how we're behind time, I'm probably going to skip this and summarize the. Okay, so since, yeah, let me say one thing where the current research frontier is. So this was classical spin ice I mentioned to you, but there's also a quantum version of spin ice, which is basically not described by magnetostatics, as I said earlier, but actually by quantum electrodynamics. So I'm going to skip all the details, but basically the kind of resonating valence bond theory that was mentioned in previous talks can also be applied to quantum spin ice. And what you find is that you get a quantum spin liquid. Effective low energy description is quantum electrodynamics now. And it's got the same mathematical form as quantum electrodynamics, but it's different in a lot of details. Okay, so one is there is more particles than our quantum electrodynamics. So you don't just have electric. So in our quantum electrodynamics, we've got electric charges like the electron, but we believe we don't have magnetic charges. So here we've got two species of charges, electric and magnetic, and therefore you've got a bigger space of behavior that you can actually probe. In particular, if you had complete dynamical access to the system, you'd expect more excitations in this system than you get in conventional electrodynamics. The speed of light is tunable. It turns out for some estimates, reasonable numbers for materials candidates, the speed of emergent light is roughly 10 meters a second. So the fastest human can outrun the speed of emergent light in spin ice. Okay. This is a dimension for quantity. As you know, the dimensionless quantity in which all the perturbation theories are controlled for quantum electrodynamics is the fine structure constant, which basically tells you how strongly electrons and photons are coupled to each other. And this is famously roughly 1/137 in quantum electrodynamics. It turns out in quantum spin ice, the fine structure constant equals 0.1. So that's more than a factor 10 bigger than in quantum electrodynamics. And you say 0.1 is still a small number. People have done perturbation theories in numbers which are considerably bigger than 0.1. But you should know that QED is believed to be unstable at around 0.2. So this is really already pretty close to the instability point of quantum electrodynamics. And it's important to realize that if quantum electrodynamics is realized in quantum spin ice, it's going to be very different from the quantum electrodynamics of everyday life. So you get Cherenkov radiation as a matter of course and not as a big exception. And so there's, if people talk about quantum emulators and quantum simulators, quantum spin ice might actually be a very good place to study strong coupling gauge theories. Okay. As a small side remark, it's very amusing that you probably know the story about the quantum Hall effect, that the original submission of Klaus von Klitzing's paper had the title Realization of a Resistance Standard Based on Natural Constants. And a very clever referee pointed out, no. In the system of constants that you have, actually what you've measured is the fine structure constant. So he changed the title of his paper. And now, as you probably know, in 2019, there was an intergovernmental conference, and Klitzing is quite proud of the fact that it was unanimously decided to change the system of constants. And he basically said the only thing that all governments in the world agree upon is the standard of units. So really, like North Korea, Hungary, the US, China, all voted for yes. And as an instance of time travel, the original title is not the correct one. Okay, so his paper was so influential that it self-corrected its mistaken title. And our small addendum to this is, so the amazing thing about the quantum Hall effect was that in a dirty semiconductor, you could actually measure the fine structure constant of QED. Now we've come full circle. In quantum spin ice, you actually have a tunable fine structure constant. So topological physics is basically giving you the opposite of what motivated in the first place. But of course, this is the big deal, and this is the small deal. Okay, so let me, before going onto my machine learning slide, let me just summarize the central result from the dynamics. So I've told you about a purely dynamical effect, this anomalous power in the noise spectrum, and it's purely dynamic. As I said, there's nothing thermodynamical that you can say about it. And what's so beautiful about it, I find, is the various layers on which different types of physics act together, so that you can use an extremely simple measurement, namely the uniform magnetization, to say something about what's going on the lattice scale. So you measure the uniform ionization in a disorder-free bulk crystal, at least one where disorder doesn't play a role. And then what you're able to say is that on that scale, on that microscopic scale, the monopoles move on a fractal structure and they move in a way that amounts to subdiffusion. Okay, so basically you've got this emergence that you start with a very simple model, namely the Ising spins. They then, by their cooperative physics, bring forth monopoles. The monopoles then have a dynamics which happens to sit near this critical point, and at the end of the day, you simply found the mechanism of generating a fractal and disorder-free system and just subdiffusion in three dimensions. Okay, the reason I didn't say all that much about machine learning is that I've got a lot of things that I'd like to do, but not actually all that much that I've actually done. So one of the things that's quite remarkable about using machine learning ideas, is also what came up in the talk today, is how far you can push things if you've got a lot of information present. So I think the determination of the critical point today was an example of if you play your cards right, you can really do some pretty amazing things. The drawback seems to be that, and this is what Alan was talking about, if you really don't have a particularly clear expectation of anything, what can you do with the data that you have? And one of the stories here is that classical Heisenberg spin liquids, in my opinion, are somewhat understudied in the sense that the first classical Heisenberg spin liquid was discovered in the late 90s, and then it remained the only example of a Heisenberg spin liquid for about 15 years. And then we proposed the second one, and then the third one, but that was still it. So until a couple of years ago, there were basically only two or three classical Heisenberg spin liquids. We now understand in some detail, which I'm not going to go into, that you can identify on some condition, under some conditions, Hamiltonians which take the form of projectors onto flat bands with correlators, that you can actually classify classical spin liquids using ideas from essentially topological band structures and ideas involving band touchings. And so using this, you can discover the various new spin liquids. So here I'm just showing you like a case of a spin liquid which has pinch points here, like a conventional spin liquid. Then you can increase the number of pinch points by nucleating a new pair. Then you can get higher order pinch points, sort of fractonic type of spin models. And then you can have a proliferation of pinch points and so on and so forth. So all of these were essentially discovered by hand, knowing what we were looking for. But there are many other types of spin liquids now that we know. So we found what we call fragile spin liquids. We've got pinch line spin liquids and so on. And so the kind of question that sort of asks itself then is there a more mechanized search possible using machine learning? That is to say, if all we have to do is essentially tell you what to look for, then there are examples of actual theory work which identifies, which uses machines to identify these spin liquids. But if I now tell you, I can give you a lot of families of Hamiltonians, can you pick out the ones which are actually distinct from the ones which we've already seen? So that would be an example of using machine learning in discovery mode. If anyone's interested in discussing this further, I'd be most happy to discuss that with you. But I think that's where the frontier has gone now. And it would be very nice if we could actually use machine learning to really discover things that we didn't know of before. Thanks for your attention.
Igor.
Roderich, you mentioned the subdiffusion in 3D. I mean, that you were looking for examples. What about the original example of Montreal and shared diffusion in amorphous semiconductors? That's where it was discovered, right? Montreal and shared paper of 1960 or 50 Xerox Corporation. That's where subdiffusion was discovered. It's electrons in amorphous semiconductor.
Yeah. Okay. So this is with disorder.
Yeah.
No, so right. So what I'm trying to say is that if you really strip things down, you basically say, I've got a regular lattice, I've got no additional structure, and nonetheless, the system manages to create a subdiffusive environment purely dynamically. So that's the thing that's new here. So I mean, there are other examples, like if you've got biosystems, if you've got tubes with surfaces,
right,
and
exactly.
But there's always some additional structure which you can identify, which then gives you this. So here in this case, if I showed you the crystal. Right, so it just looks like it just looks like localized Ising spins, which don't do anything particular, and then you find that there's actually.
Right. So am I right thinking that this is actually a normal diffusion just in a fractal structure?
Because I agree with the sentence up to the word "this is just."
No, No, no,
I agree, you have summarized our understanding correctly, but the understanding is very non-trivial.
Right. I mean, it's just that, the subdiffusion in time direction is actually.
That's right, it's inherited from the spatial structure of the
Yes.
fractal.
Right.
And the fractal itself is a purely dynamical
Yeah.
phenomenon. Okay.
So I actually have a related question. So the dynamics is the level of a single monopole.
Right?
What if you have finite density of monopoles and anti-monopoles, so that processes like annihilation and creation
Okay.
along?
So annihilation and creation don't really make, so the global answer to this is there are many ways of cutting this off right now. In simulations, the main cutoff is actually that you're not sitting exactly at percolation. If you've got a high density of monopoles, then one monopole passing will unblock some things. So this would be another mechanism for cutting things off. It actually is operational at some point. So you saw that this 1.5 goes away when you go to 1.2 Kelvin. This probably already is a contributing factor there. Then what plays the leading role is a question of.
But then if you increase temperature, you would increase the density of these things. Then
That's right, and it goes away. Signal goes away. So it's something that you see in the further down the temperature. Yeah, thank you for the question.
More questions? Alan?
Do you have a clear idea of all the Hamiltonian terms you would want and what lattices you would want to do a bit search on?
Well, I think the idea would be to start off with some reasonably near neighbor Hamiltonians with, which like in these, where you write down the kind of anisotropies that are natural. And, then the question is how many parameters do you actually want to go over? I mean, here we typically had Hamiltonians which only had like 2 or 3 parameters, which is one mean we really did it by hand. We said, what's the simplest thing that we can see these? But once you start asking, what are natural Hamiltonians which might appear in experiment, then it would make sense to actually search over those.
And we did a really robust kind of thing that's found in the ground state. We did a really robust.
Yeah, I mean, so most of this was large n-type theories, which I presume you've implemented already. So I think it's much more, getting the machine learning to look for things that you're not telling it to. So it's unsupervised learning.
Yeah.
I think that's probably the
Also,
heart of
the
it.
space representation that you're doing.
Yeah.
You're also getting the things we can do the case space and the blue space representation.
More questions? If not, let's thank our speakers.